Two 5-digit positive integers are formed using each of the digits 0 through 9 once. What is the smallest possible positive difference between the two integers? All right, well, let's call the integers a, b, c, d, e, and then f, g, h, I, j. And then when you subtract them, obviously, you're subtracting the first digits, which are the 10,000, so a minus f. And then you would be subtracting the 1,000 numbers, which are b minus g. And then the 100 guys, which are c minus h. And then you'll be subtracting the tens numbers, which are d and I. And then finally the units digits, which are e minus j. So this is the difference, d for difference. Now we want this to be smallest as possible. Okay, so let's talk about this one at a time. How can I make this as small as possible? I can't make it negative because it's got to be positive. Okay, so that's out. I can't make it negative. Can I make it 0? Well, that's a tempting thing to do, but the problem is that we can only use each of these digits once. To make it 0, this would have to be equal. A would have to equal f. So, for example, 3 and 3 or 4 and 4, but I can't do that. Okay, can't do that. So the only thing I can do is make this equal to 1. That's the smallest. All right, so this has to equal 1, a minus f. So I hope that logic makes sense. Now, these guys, however, I can make them negative, because once I make those negative, then this minus a bunch of negatives will still be positive, but it should be as small as possible. Okay, so we have to make these negative, and we want to make them as negative as possible. So b minus g, I want to make that as big as I can. Okay, well, the biggest I could possibly make it is 9 minus 0, or 0 minus 9. That way, 0 minus 9. Now let's turn our attention to c minus h, this guy right here. Again, I want to make it as negative as possible. Let's choose the biggest difference, 1 and 8. So 1 minus 8. Same philosophy on the next one, d minus I, 2 and 7. So 2 minus 7. Trying to make it as negative as possible. And the last one, 3 and 6. Yeah. And therefore, the only numbers that are left are 4 and 5. So I put that here, 5 minus 4. Okay, great. So now let's figure out what were these numbers. Based on my selections, what numbers did I make? I made 5, 0, 1, 2, 3. And the other number I made 4, 9, 8, 7, 6. And when you subtract these two, you get 247. There you go. The answer to number 21 is C. Two joggers each run at their own constant speed and in opposite directions from one another around an oval track. They meet every 36 seconds. The first jogger completes one lap of the track in a time that, when measured in seconds, is a number, not necessarily an integer, between 80 and 100. The second jogger completes one lap of the track in a time t seconds where t is a positive integer. The product of the smallest and largest possible integer values of t is. All right. Let's draw a little diagram. Here's our oval track. And let's say this is the start line. And the first guy is R1. He's going in that direction. And the second guy is R2. And he's going in the opposite direction. And eventually somewhere, I don't know where, but let's say they meet right here. R1, R2 eventually comes here, and so does R1. They meet there. And that happens for the first time at 36 seconds, right? Because they meet every 36 seconds. So let's label the distance from there to there. Let's just call it X. And the total distance, I will just call D. Might as well. So that means the distance from here to here is going to be D minus X. All right. So throughout this question, of course, we are using speed is equal to distance over time, or any variations such as distance over speed is equal to time. Okay, so let's figure this out now. From the first one, for R1, his distance is x, and his speed I'll call S1. And for the second runner, his distance is d minus x, and for his speed I'll call it S2. And these are written in this format. So they both represent times, but the times are equal. They're basically equal to 36. So these are equal, and they both equal 36. Okay. So from these equations, we get the following, that x is equal to 36 S1. And from the other one, d minus x is equal to 36 S2. Okay. So d is equal to 36 S2 plus x, but x is 36 S1. So I can put that in here. D is equal to 36 S2 plus 36 S1. All right. So far, so good. And let's keep going with this information. Now, the question tells us something important, that the time for the first runner, the first jogger, is between 80 and 100. So what is that time? If you were to write it, it's d over s, right? Where d for the first runner is d minus x. Sorry, not d minus x. The d that we are talking about in this case is one full lap of the track for the first jogger. So one full lap of the track is just d. And the equation that we're using is this one. So we have to divide by the speed, which for the first jogger would be S1. And they're saying that is between 100 and 80. So one full lap of the track. All right. And for the second guy, the second runner, for him, it's also using this formula right here. And that formula basically is d over S2. And they're calling that t, small t, and they're saying that is equal to an integer. All right, so we have to now work with this. All right, well, let's work with this guy right here. D, we just figured out right here, so let's substitute that in. And this should be 80, actually. So we got 80 less than D, which is 36 S1 plus 36 S2, all over S1, less than 100. Well, if we break it up, it will be 36 plus 36 S2 over S1, less than 100. Bring the 36 over to the other sides, and when you do, you'll get, let's see here, 64 here and 44 here. Okay. Now divide both sides by 36, and you get S2 over S1 is 64 over 36 and 44 over 36. So no tricks, just basic algebra. Now at this point, I want to get it something like this. I have to figure out this. It looks sort of like that, but not quite, right? So I've got to make it like that. Well, the first thing I got to do is flip it because S2 is on the bottom here. Okay, let's do that. So I got to flip it. So if I flip it, it becomes S1 over S2, and these signs also flip. So this becomes 36 over 44, and this becomes 36 over 64. Now my goal is to make it look like t. I can do that, of course, I have to multiply through by d. So this becomes 36 d over S2 times S1, 36d. This is over 64, this is over 44, and the last step is I got to divide through by S1. Now we got to divide through by S1, so this will become 36 over 44, d over S1. This will become d over S2, and this will become 36 over 64, d over S1. So let's bring this up here, and that middle term right here, d over S2, is basically our t. So I'll put that in the middle instead of the other expression. And this is 36 over 64, d over S1. And it's on this side 36 over 44, d over S1. Now, here's where we figure out the max and min for t. And we've got two choices, right? If we remember in the question, I'll put this in brackets, and it's up here actually. right here, that d over S1 is between 80 and 100. So what do I put here and what do I put here? And that is probably a little tricky part of the question. I'm going to do both. I'm going to calculate it with, first, let's say I put 100 here, this part of the boundary, and I'm going to put 80 on this side. And let's see what we get. If we put these numbers, t comes out to be greater than 45, exactly 45, and less than 81.8. So that basically means that the smallest that t can be is 46, and the largest is 81. So they want you to figure out the product. So the product would be 46 times 81, and that is 3726. Okay, let's see if that's one of the answer choices. 3726 is not. All right, let's go back to the drawing board. Instead of putting 180, let's flip it. So that's perfectly fine. It's a good thing that that's not one of the answer choices, because that's the wrong answer. So put 36 over 44, but this time put 80 here. And on this side, we can put 36 over 64 times 100. When you do this math, t becomes between 56.25 and 65.45. So this means that the smallest that t can be in terms of an integer, because remember, it's an integer, is 56, or 57 actually. And the largest it can be is 65. So now this product is 57 times 65, and that product, 57 times 65, is 3705. And that is the correct answer. It is in the answer choices, answer choice A for number 24. A collection of coins includes only pennies, nickels, dimes, and quarters. Using the coins in this collection, it is possible to create any amount of money less than $1. What is the smallest possible number of coins in this collection? Well, to create sums anywhere, I guess, from 0 to 4, you need at least 4 pennies, right? That is mandatory. Then to create a sum anywhere from 5 to 9, you would need an additional 1 nickel, because if you take any of these sums and add the nickel, you'll be able to get a sum from 5 to 9. So like, for example, you had 2 pennies, you add a nickel, you get 7 cents, and that's in that range. Now let's go to the next range, 10 to 19. What else do I need to create? Well, 10 to 19, obviously I need a dime. If I take any of the sums that I've created here and add a dime, I'll get up to this range. Now we get up to this range, 20 to 24. That's a unique one in the sense that it's a smaller range than 10 to 19, right? I didn't get into a bigger zone because I need 1 more nickel for that. Now, the good news is we can now go up by 25s. 25 to 49, all I need is a quarter. And I can take any of the sums in here, add 25, and I will get into this range. In a very similar way, any of the sums that are between 50 and 74, I can create by adding another quarter. And finally, from 75 to 99, because they're saying less than $1, right? So up to 99, you would just need 1 more quarter. And the good news is that just with these coins, you can create any of the sums from, 0 to 99. So how many coins do I have? I got 4, 5, 6, 7, 8, 9, 10. 10 coins is all you need. So number 21, the answer is A. Starting with the input mn, machine A gives an output of nm. Starting with the input mn, machine B gives the output m plus 3n n. Starting with the input mn, machine C gives the output m minus 2n n. Natalie starts with the pair 0, 1 and inputs into one of the machines. She takes the output and inputs it into any one of the machines. she continues to take the output and receives and inputs it into any of the machines. For example, starting with 0, 1, she could use machines B, B, A, C, B in that order to obtain the output 7, 6. Which of the following pairs is impossible for her to obtain after repeating this process any number of times? Let's start with the pair that they have given us, and let's just see what it looks like. When you put it through A, obviously it just flips. If you put this through B, it will become 3, 1, where this is the formula, m plus 3n, n. And if you put this through C, it will become minus 2, 1, m minus 2n, n. And do you see any kind of pattern? Not really, right? You say, well, I have no idea. This doesn't really help me. So 0, 1 is not really going to be very beneficial to try to look for any kind of scenario. So what I'm going to do is choose something else. And you can choose anything, and it should work for anything of what I'm trying to show. I'm going to choose 3, 6 for my initial mn. And let's see what happens. Now, what we are really interested in talking about is something called the GCF, greatest common factor. And in this case, the greatest common factor for 3 and 6 is 3. And you will see that all the outputs will also have a greatest common factor of 3. So let's first figure out the outputs. A was just going to be 6, 3. So I think that's pretty obvious. But what about if I go through this machine? That gives me 21 and 6. And if I go through C, it gives me minus 9 and 6. And I hope you're convinced that all the outputs also have a GCF of 3. So that is the key to the question, basically, that the greatest common factor will be maintained as you go through these machines, no matter what the original pair is. So now we go back to our question, which is 0, 1. What is the GCF of 0, 1? Well, it's just 1. Unfortunately, it's that simple or boring, because the greatest common factor of 0 and 1 is 1. The factor of 1 is just 1. And 0, well, anything is a factor of 0, right? So the GCF here is 1. So what we are asked to do is somehow eventually come up with one of these, right? So that means that anything you come up with will also have to have a GCF of 1. So whatever, it doesn't matter what order, how many times you do it, multiple times over, at the very end, whatever you come up with also must have a GCF of 1. So then we have to now look at the answer choices. Which one of these has a GCF of 1? Okay, to do that, we've got to look at each number. So fortunately, there's not too many. There's only 5 plus 1, 6 numbers we have to look at. So the first one, 2009, and if we break that up into prime factors, it's 7 times 7 times 41. The next one is going to be 1016, and that is 2 times 2 times 2 times 127. This is the prime factors. Next one is 1004. That is 2 times 2 times 251 as its prime factors. 1002 in the answer choices. 2 times 3 times 167. Then 1008. That is 2 times 2 times 2 times 2 times 3 times 3 times 7. And last one is 1032, and that is 2 times 2 times 2 times 3 times 43. So that is the common factors of everything. Well, that is the factors of everything, not the common factors. Okay, now we have to now compare everything with 2009, keeping in mind do we have a GCF of 1. And if you do compare any of these 5 numbers with 2009, you'll notice that all of them have a GCF of 1 with 2009, except 1008, because 1008 has a GCF of 7. So that means that since it has a GCF of 7, 1008 and 2009, it cannot go here as an output. Why? Because you're starting with 0, 1. The output must have a GCF of 1. If you put 2008 and 2009 and 1008 here, that won't work because these two have a GCF of 7. And there's no way to get a GCF of 7 if you're starting with 0, 1, because the GCF is maintained throughout this process. So that is the only one that is not possible. All the other ones can be placed in there as an output. So, number 24, the answer is D. A box contains a total of 400 tickets that come in 5 colors: blue, green, red, yellow, and orange. The ratio of blue to green to red tickets is 1 to 2 to 4. So I'll call it X to 2X to 4X. The ratio of green to yellow to orange is 1 to 3 to 6. So the ratio of green to yellow to orange is 1 to 3 to 6. So I will write Z, 3Z, 6Z. What is the smallest number of tickets that must be drawn to ensure that at least 50 tickets of one color have been selected? All right. So the first thing we have to do is find out the distribution of these tickets, considering that they all add up to 400. Well, Z represents the number of green tickets, but so does 2X. So that means that 2X is equal to Z. If 2X is equal to Z, that means X is equal to Z over 2. So put that here. 4X would be equal to 2Z. So put that here. And then 3Z would be equal to 6X. So put that here. And 6Z will be equivalent of 12X. So put that here. So I can add all these guys up. And if I do, that will equal 400. So X plus 2X plus 4X plus 6X plus 12X is equal to 400. So what does that give me? 3, 7, 13, and 25. So 25X is equal to 400. So that means X is 16. So I'll plug those numbers back into here. So that means we've got 16 for blue, we've got 32 for green, 4X is 64, 6X is 96, and 12X is 192. So that's the number of tickets of each color. Now our task is the final sentence. What is the smallest number of tickets that must be drawn to ensure that at least 50 tickets of one color have been selected? Notice the spelling of the word color. Now you can tell it's a Canadian math contest. All right, so let's use extreme case scenarios here. We want to use the smallest number of tickets. Now, some of you might say, well, just choose 50 tickets. That's the smallest number, and it's the smallest of the answer choices. But here's the thing. If I choose 50, it doesn't ensure that I get 50 of the same color. Let's say I chose 50, but it was a few of them were green, and a few of them were red, and a few of them were yellow. That doesn't ensure. I have to guarantee. Now, how do I do that? And this is the way you do it. First, what you do is you select all of the blues. So that's 16 of them. So we've exhausted the blues. Now we select all of the green. That's 32. We're done. We've taken all the greens out. right? Now, we can't choose them, meaning we can't look and see that we're choosing them. But what I'm saying is this is the extreme case scenario that just by chance, when you selected 16, all of them happened to be blue. Then you selected another 32, and all of them happened to be green. It's an extreme case scenario. Now what we do is we say, okay, I'm not guaranteed of having the same color. I'm going to select 49 now of the red. And just by some chance, they all happen to be red. Then I'm going to select another 49 tickets, and by chance, they're all going to be yellow. And then I'm going to select another 49, and by chance, they're all going to be orange. The reason I'm doing it like this is because I have to guarantee that when I choose a certain number of tickets, that there's going to be 50 of the same color. This scenario does not produce 50 of the same color. You see what I mean? So this scenario is possible. And we have to look at any extreme case scenario where it's possible to not have 50. This is a possible scenario where I chose 16 blue, I chose 32 green, 49 were red, 49 were yellow, and 49 were orange. So let's add these up, and when you do, you get 195. So far, in this extreme case scenario, we don't have 50 of any one color, but the very next ticket that's chosen will push me to 50. It won't be a blue or a green because those are exhausted. Those have already been all selected. But the very next ticket I choose must end up being either a red, yellow, or orange because there still are some of those left, right? Because 64, 96, and 192 are the total, and I only chose 49 of each of them. So the very next one, let's say if it's an R, a red ticket, boom, I've got 50 of them. If the very next one happened to be a yellow, I've got 50 of yellow. If the very next ticket happened to be an orange, I've got 50 oranges. Oh, 50 orange tickets. So 195 plus the very next ticket, and that would be 196. So it's a good little challenge in terms of counting. And therefore, number 25, the answer is D.